Honored to be here today. I would like to thank the organizing committee and in particular the Dr. Jitendra Pandey to give me the opportunity of present part of my work here for my first time in India. So thank you very much. So actually I'm an associate professor at Rennes University in the west part of France, here about 2 hours from Paris, and Rennes is a really beautiful city and also near the sea. So I hope to meet you there. Can you hear me? Yes? Okay. No? Is it working? Yeah. Okay, so my research is dedicated to membrane science. Maybe not all of you are familiar with this, so I will first introduce what the membrane is. So a membrane is a thin layer of material which is semi-permeable or perm-selective. When you apply driving force through a membrane, you can basically separate molecules according to their size and their physico-chemical properties. You will thus obtain two fractions. The first one is the retentate, with the molecule retained by the membrane, while the other side you have the permeate with the molecule passing through the membrane. This can be applied for gas and liquid, but I will only focus on liquid today. So, according to the driving force you apply to the membrane, then you can classify the membrane processes in different families. When you are working with a pressure difference across the membrane, then you have microfiltration, ultrafiltration, nanofiltration, or reverse osmosis process. If you apply a chemical potential difference, then you have a forward osmosis process. Electrical potential difference, then you will have electrodialysis. And the difference of vapor pressure, then you will talk about membrane distillation or membrane pervaporation. Actually, my research is focused on pressure-driven processes and membrane distillation, but I will only talk about pressure-driven processes today. So, as I said, different type of filtration processes that will be able to separate different compounds, to retain different compounds according to their size and also physico-chemical properties, but mostly their size. Here, with microfiltration, you will retain bacteria, particles. With ultrafiltration, smaller colloids or macromolecules. With nanofiltration, multivalent ion or soluble organic compounds. And with reverse osmosis, you will retain monovalent ions, and you can just use it to desalinate water, for example. So membranes are made of inorganic materials, which are ceramic. They are very resistant both to high temperature and really hard chemical conditions, but they are really expensive. So you can also use polymeric membranes, which are much lower cost, which have more lower cost, and are also more easy to produce. But of course, they are less resistant. But actually, these membranes, polymeric membranes, are the most used in the industry, and they can be made of a number of polymers, including polyether sulfone or polyamide, cellulose acetate, etc. So I will focus on that today. These membranes are mostly used in water treatment for drinking water production, to remove bacteria, viruses, natural organic matter, metals, heavy metals, micropollutants. They can also be used to treat wastewater in membrane bioreactors. I will come back on that a bit later. And you can also use them for seawater desalination, but also in other fields like food industry for dairy production or wine filtration, for example, biotechnology, chemical, pharmaceutical industry, of course, also in petroleum industry, etc. So, but membrane processes have a major drawback, and this major drawback is membrane fouling. That is to say, the accumulation of matter on the membrane surface or inside the pores of the membrane. This can happen due to different mechanisms, including adsorption, cake formation, deposit formation. This cake can also be a biocake with bacteria or biofilm. Also pore blocking here. And of course, all these mechanisms usually appears all together, and you then have a complex picture of fouling. The consequences are a reduction of process efficiency and increase in energy consumption and environmental impact of your project, of your process. Sorry. So fouling is a complex phenomenon which involves many parameters which can be classified in 3 different families, including fluid properties, the composition, the chemistry of the fluid, membrane properties, the material of course, but also structural properties, pore size, porosity, etc. Or physico-chemical properties, surface charge, hydrophilicity, and of course it will also depend on the operating condition, the duration of filtration cycle, the transmembrane pressure you apply to get your flux, etc. So it's a complex phenomenon, and it has to be mitigated or eliminated because otherwise your process cannot work properly. So now, if we focus on a particular case of membrane bioreactors that are used to treat wastewater, basically a membrane bioreactor for wastewater treatment is a bioreactor in which your bacteria will eat the pollutant, so mainly carbon, and then you will have your clean water but with bacteria. And what you want to do is to separate the water from the bacteria, and to do that you can use a membrane, and then you get your membrane bioreactor. So the biofluid is something really complex in your bioreactor with sludge particles, that is to say bacteria, aggregates of bacteria, flocks, also colloids, and also dissolved species, which can come from either the wastewater itself or can be produced by the bacteria. So if you filter this complex biofluid, of course you will obtain a complex fouling layer. And this fouling layer has a really high resistance, hydraulic resistance, which means that it will contribute to reduce your flux, and it's also highly compressible, which means that if your flux is decreasing and you want to maintain it, if you double here the transmembrane pressure, you will not be able to double the flux, your permeate flux, because the resistance will increase. So it's another big problem with the high resistance. So if you want to mitigate the fouling, that is to say to reduce or delay the impact of fouling, you can play on the different parameters I mentioned before. And what I'm interested in is playing with the fluid properties and the use of additives. These additives might be salt, flocculant, absorbent, and also polymeric particles. Actually, my colleague here, Benoît Technet, some years ago had the idea to add particles inside polystyrene particles, inside the biofluid, and to filter this mix instead of filtering the biofluid. And what he could observe is that the flux was higher, so the cake resistance was lowered, and also the cake was less compressible. So of course that was really interesting, but if you want to apply this to a much larger scale, then you have to understand why these two things happen. And this is what a topic I worked on for several years, and the idea was to try to see if this modification of parameter was due to structural effects. I mean, are the bacteria, are the particles changing the structure of the deposit you make, the deposit that appear on the membrane, or was it due to adsorption effects of some soluble compounds on the particles that then will prevent membrane fouling. So to obtain some information about that and be able to dissociate the different contributions, I actually used a technique developed in INSA Toulouse, where I meet Benoît, as I said before, to characterize in situ the foulant cake growth during filtration with a non-invasive technique, and also giving information about the structure. So this technique is quite simple actually. You need your membrane, of course, a laser sheet, and a CCD camera. When the membrane is virgin, your laser sheet will be deflected on a certain location that you can monitor with your CCD camera. Now, if a cake is growing, there will be a shift of the deflection position here, and if you are able to measure the shift and if you know the angle of incidence of the laser sheet, then you can calculate the thickness of your deposit. And here we are talking about a thickness with a resolution of 3 micrometers. So you can see really in detail what happened on membrane surface during filtration, and of course this technique is non-destructive, so it's really interesting. I also play a bit with LC, OCD, OND technique, which is an advanced fluid characterization that allows to detect which type of organic compounds are in your biofluid. Actually, it's a liquid chromatography with an organic carbon detector, organic nitrogen detector, and also UV detector. And what we could see, what we observed is that when we filtrate the sludge, we had this resistance, the biofluid sludge. We have this resistance in blue that increased during filtration, which is the resistance of the fouling layer. But if we add the particles before the filtration in the biofluid, and if we filter this mix between the particle and the biofluid, the resistance is almost 2 times lower than when filtering the biofluid alone. So this is interesting. This means that your flux in red here will be higher when you add the particles than when you don't have the particle. So this was an interesting point. But now we had to understand why. Oh, sorry. And actually, if you monitor the cake growth on time, what you can see is that when you filter the sludge alone, the cake is really thin and really compact. And actually, the cake thickness was lower than the size of the flocks that were depositing on membrane, so showing that these flocks were compressed on membrane surface. On the other hand, if you filter the mix between the sludge and particle, the cake was much higher and growing much thicker. So if you have a thicker cake but more permeable cake, that means that your cake is probably more porous. So this is an interesting point. Now, if we focus on the adsorption of organic compounds onto the particles, what we could see is that we have a change in the removal mechanism of your pollutants, of your organic compounds. Actually, the cake is made of the sludge flocks, the bacteria, plus some organic soluble species retained by the membrane when you filter the biofluid alone. So it's here in blue. Okay, but now if you add the particles, you have almost the same elimination of your pollutants, of your organic compounds, but the mechanism have a bit shift, and part of the organic matter is removed by adsorption onto the particles. And also you can remove compounds that you were not able to remove only by filtration because they were too small to be retained by the membrane. And if these organic compounds adsorb on the membrane, they won't on the particles. Sorry, they won't deposit it on the membrane. So, if you calculate the amount of organic carbon deposited on your membrane when you filter the sludge alone, it's around 72 milligrams of organic carbon per square meter. And when you add the particle, you have only about 40 milligrams of carbon per square meter. That means that the deposit is containing less foulant species. So this is interesting, and actually what we could also see is that we could change the composition of the biocake because when we were filtering sludge alone, the cake was made of mostly humic substances, while it was mostly made of biopolymers in the case of the filtration of the mix between the particles and the biological fluid. Biopolymer here means protein and also polysaccharides that are actually produced by the bacteria. So with this technique we can modify the cake structure, we can also modify the cake composition. That means that it opens the way towards Foulant cake engineering. Maybe it will be possible in the near future to control the cake structure and also its composition in order to minimize the impact of cake buildup on process performances. With this idea, the cake is still growing, but you can control its structure and its properties in order that it does not cause too much trouble to your processes. Okay, but when you do that, you don't eliminate totally fouling. What we could see is that the flux was still decreasing. At the end, we still have fouling. So we still need for periodical fouling layer removal. And if you mitigate, you can, let's say, reduce the frequency of this periodical fouling layer removal, but you cannot avoid them. And if you do that, usually you use backwash, that is to say you send water from the permeate side to the feed side, but you cannot remove all your foulant. So usually what you do is then you use chemicals, and in particular you use oxidants such as sodium hypochlorite solution. But this might have some consequence on the membrane material if you use polymeric membrane. And this is something we are also studying. Actually, sodium hypochlorite solution, the bleach, for example, are really used because they are really efficient, also really cheap, but we know that they are responsible for membrane degradation. Here you have a picture, same picture of the top surface of a pristine membrane, and you can see that after exposure to bleach, some cracks appear on the membrane, which leads to a decrease of membrane retention ability, stronger membrane fouling, etc. So we have to understand the degradation mechanism of this material, of the membrane material, and also to understand which species are involved in the molecular degradation of the membrane. So we are studying this for polyether sulfone, PES membrane, which are really widely used in water treatment because of their good chemical and mechanical resistance. However, one drawback is that they are relatively hydrophobic, and so you have to add hydrophilic additive inside your membrane, and usually what you do is you add PVP here to have higher fluxes when using your membrane to filter water. We age this membrane. We do this artificially with an accelerated aging protocol on the basis of a commercial membrane, and we characterize the membrane before and after the aging procedure. We use different techniques, including FTIR, and what we can see is that after aging, here a small band appears on your spectra, and this small band is located at a wave number of around 1030 centimeter minus 1, and actually it has been reported in the literature that this band could be due to the formation of sulfonate groups